Okay, last time we worked on some examples. We're going to continue those examples. And I wanted to continue here with the inclined plane and demonstrate this a little bit. Again, you can have lots of cases. You can have static equilibrium or dynamic equilibrium. It doesn't mean, again, equilibrium doesn't mean you're not moving. You could be sliding up or down at a constant rate. Or you can have acceleration not zero. And again, we'll tie some other ropes to that. I wanted to show this nice little question. At what angle will it start to slide? So we come over here to our ramp. We have a nice little cool little piece of engineering here, just simple little bob, as we call it. Anything that hangs down is a bob. And I've got a block. And so what I'm going to do is try to find out what angle it will start to slide. I'm good, I'm good, I'm good, I'm good. And this is one way to calculate the coefficient of which friction? Static, right? Just right in there. Notice the acceleration is 0. It's just barely. I've got some ridges. What if I change one of the surfaces? Now it slides, right? So it's a different coefficient of static friction. And you can calculate that very easily. Again, the choice of friction you would use is static max. You just set it in there. Just set it up. Here's the thing. Just set it up and realize that you're going to solve once you set it up. Don't worry about solving it first. What's the condition? Well, the accelerations are 0. I've got static max. I've got normal and friction, in this case holding it up, and gravity. And that's it. So go about that. And of course, it'll depend on what object. Now, for this guy, if I'm going to look for that maximum angle, it's still too much, still too much. So for that surface, which is smoother, I've got a smaller angle. And the fun thing would be to calculate it in wood on wood, maybe look up a table, measure it. That's kind of cool. You can put it on wheels, you can connect it with things, you can do erasers, and that sort of thing. So the next little bit of puzzles will be with ropes and strings. And clever sailors know about ropes and strings, and they may not know how to calculate stuff, but they'll wrap stuff up and have a good intuition. Our model is that everywhere in the string or rope has the same strength of tension T. That'll work for us now. So take a look at this case. There's a few little puzzles that make you scratch your head. That's the cool thing, is that this will take you beyond what your intuition can take you. So suppose your foot's in traction. We've got a pulley here, a pulley here. Our pulleys for now have negligible mass and negligible friction. I've drawn a purple rope and a green rope. So how do I do this? Well, my question is, how much traction is that leg in? Now this one's tricky. This one really challenges you to choose your receiver. So I'm just going to walk through this. I want to know this. I'm going to have to backtrack. Puzzles. Solving puzzles is about thinking physics and asking yourself, what do I know? What's true here? What can I certainly say? For example, I can certainly say, if this is all static, that the force of tension, purple, balances the force of gravity on A. MAG. So I know now the tension in the purple rope. One rope here, if I cut it, it'll drop. Fine. I wrap it around and I go this way. If I cut it here, not happy. If I cut it here, also not happy. So if I think about it, the purple is now up here on this pulley, pulling to the right and to the right. So I've got two TPs to the right. So what's the green? It's a different rope. Well, the green tension, I better balance that or else I'm in trouble. So T green is certainly equal to 2t purple. Now I caution you to don't solve too soon, but I want to walk you through this kind of quickly. Okay. And now that's happening over here. That's t green. But if I look at my broken ankle in a cast, that's what that's supposed to be, it's being pulled to the right by green. This pulley was pulled to the left by green and to the right by 2 purples. Now my ankle is being pulled to the right by green, which is equal to 2TP, and TP is equal to that. Isn't that cool? But my ankle hopefully isn't accelerating. That would be a problem. Therefore, it has to be pulled this way by my leg, force leg, and that means that my leg must be pulled that way by force leg. So it's pretty cool. It takes training. You wouldn't be expected to just figure that out, but hopefully that helps you, that little example. Another neat one is imagine climbing a rope. If you climb a rope, you grab onto that rope. And what do? You push it down. Just like if I want to jump, I push the ground down, the ground pushes me up. So watch this. What made me jump? The ground. The ground pushed on me, it pushed me up. You know, if it just did it right now without me doing anything, that'd be weird. But if you push it, in space, you push off some gas, it goes that way, you go that way. If I push down on the rope, it'll push up on me. So by climbing, that's kind of neat. Now you're painting or something precariously. Big old, here's some surface here, a pulley attached here, and you're grabbing onto the rope. This one's a little tricky in isolating the object. So the object, again, I'm going to do in blue, and that's going to be you and this platform. So that whole thing. Now, what are the forces? Well, what's touching? What's touching is the rope in 2 places. So I've got, all right, fine, mg, force of gravity near the surface of Earth. And I've got 2 tensions, right? Because if you cut here, you're not going to be happy. And if you cut here, you're not going to be happy. So that's force of 2 tensions in that rope. T, T, same rope. All right? So if the rope is pulling you up, you pull it down. The strength that you pull it down is here. But you also get it over here. So pulleys are kind of cool that way. Right? So think about that. That means that in this case, if you're just sitting there, or dynamic equilibrium, still no acceleration, then 2t have to equal the mg. So that's kind of neat. And how about this one? A little harder to see the way I've drawn it over here. Suppose I want to hold something up. Well, does this do anything if I wrap a pulley here, wrap a pulley here, wrap a pulley here? Does that do anything? I mean, what does that object feel? It feels 1t, right? So not so interesting. And finally, let's take a look at a case where it is useful over here. So the neat thing is that when you wrap, if you here, my lower hand's being pulled up by 1t. Here, this rod is being pulled by 2t. Just thinking of cutting it, and it'll snap, right? So it's got 2t. Now, if I wrap, right, as sailors often do, and many people do, I've got to pull here, I've got to pull down over here, I've got to pull over here, because again, if I cut it, it'll snap. I've got to pull down here, and I pull down over here. So I've got 2 and 2. 1 wrap, I get 2. 2 wraps, I get 4 T's going on this guy. So that's pretty neat. If I go over here, and I have this set up, notice what I've got. I've got 100 grams and 50 grams plus a little. Why doesn't it work with 150? Whoa, it doesn't work. Well, let's take a look. This system is being pulled up by 1, 2 T's. This over here is a T, but that's not direct, that's over here. This over here, if I look at the pulley, whatever, I got 2 T's on the pulley, but that's, I got 1 T over here. So I got 1 T on half the mass. I got 2 T's on twice the mass. Why doesn't it balance? Because this has mass. So in order to balance that, in other words, the force diagram here is 2 T's and M of this object plus the M of the pulley, G times G down. So 2 T's equals this mass times G. 1 T is this mass times G. About half the mass supported by, and twice the mass supported by half the mass. So it makes it easier to pull instead of directly lifting this. And you could imagine if I keep doing that, I could easily lift things with pulleys and ropes. Okay, I think that should get you going. The next topic is connected objects, 2 objects connected by a rope, and then we're going to go into circular motion. All right.